Welcome to our discussion on measuring total energy change within a system. In this lesson, we will define molar heat, calculate energy used or released during a phase change, and graph and calculate total energy transferred during both single phases and phase changes. The first thing we need to look at is measuring energy during a phase change, because as we've already talked about, during a phase change, the temperature of a substance does not change. And that's because even though energy is being continually added or released, that energy is now going to either making or breaking bonds of that substance to allow it to change phase. So when we measure the energy change during a phase change, we typically measure it in terms of 1 mole, and this is called the molar heat, and its units are kilojoules per mole. So it's the amount of heat required or released by 1 mole of a substance as it changes phase. Now let's take a look at our molar heats for each of the following scenarios. So first we have the phase change from solid to liquid. This is our delta H of fusion, or our molar heat of fusion, which is the heat required by 1 mole of a substance to melt or to change phase from solid to liquid. And we write this as delta H fuss for shorthand. For example, the molar heat of fusion, or the delta H fuss for water, is 6.01 kilojoules per mole, meaning that it takes 6.01 kilojoules for every mole of water to change its phase from solid to liquid. And this is a good value to have written down in your notes, as it's the one we're going to use most commonly. Now let's take a look at going from liquid to gas. The heat required to vaporize, or to go from liquid to gas, for 1 mole of a substance is our delta H of vaporization, or our delta H vap. So for example, our delta H vap of water is 40.7 kilojoules per mole, meaning that 40.7 kilojoules is required to vaporize 1 mole of water, or to take 1 mole of water from a liquid state to a gas state. This is also another good value to have in your notes, as we will use this quite frequently. Next, for going from gas to a liquid, we're going to use our delta H condensation, or our molar heat of condensation, which is our delta H cond for short. So for this one, this is actually the amount of heat released by 1 mole of a substance to condense. So for example, for water, our delta H cond is actually negative 40.7 kilojoules per mole. It's the same amount of energy required to go from liquid to a gas, but now because we're going from gas to liquid, we're releasing that heat rather than absorbing it. So we have to denote that by making our delta H cond value for water negative, or really any of our delta H cond values are going to be negative because we're releasing heat rather than absorbing it. So finally, when we go from liquid to a solid, we're also releasing heat, and this is our molar heat of solidification, or delta H solid, which is how much heat is released to solidify 1 mole of a substance. So once again, as we saw with our delta H cond, our delta H solid, or delta H SOL, is going to be the negative value of the opposite phase of going from solid to liquid. So for water, for example, our delta H solid is going to be negative 6.01 kilojoules per mole, meaning that we're going to release 6.01 kilojoules for every mole of water that solidifies or changes phase from liquid to solid. So let's take a look at that heating and cooling curve of water again, but let's fill in all of our molar heats at all of our phase changes. So as I go from -5 to 0, I'd be in one phase. I would be solid if this was water, between -5 degrees Celsius and 0 degrees Celsius. Once I get to 0, if I'm adding heat, I'm going to change phase from solid to a liquid. So right here, to calculate this piece, I would need to use my delta H fuss. Now, as I continue to add energy, I would fully melt and become a liquid. So for this next piece, I would be in the liquid phase. And then finally, when my temperature reached 100 degrees, I would have another phase change. And since I'm going from liquid to gas, to calculate the energy change here, I would use my delta H vap. Now, if I was removing energy and starting at 105 degrees Celsius and removing energy in order to go from a gas to a liquid to a solid, I would have my other molar heats. So from 105 to 100, I would just be in the gaseous phase. And then once I got back to that 100 degrees Celsius, that's my phase change point for water. And at this point, since I'm releasing heat, I would be going from gas to liquid. So to calculate the energy change there, I would use my delta H cond, or my delta H for condensation. Then once my phase change has been completed, I would then be in the liquid phase once again, and I'm continuing to remove energy, and then my temperature would decrease back down to 0 degrees Celsius, where I would hit another phase change point. And at that point, to calculate the amount of energy used during that phase change to go from liquid to solid, I would need to use my delta H solid for that point, that phase change. So looking at this graph, we now know how to measure the energy during a phase change that's either absorbed or released. But what about measuring energy during a single phase? So when we're only a solid or a liquid or a gas. Well, notice for each one of those pieces, we have a temperature change. So whenever we have a temperature change, we can actually measure our energy absorbed or released by using Q equals MCAT. So anytime you're in a single phase where you have a temperature change, you can use Q equals MCAT. However, when you have a phase change and there is no change in temperature, that's when you have to use your molar heats or your delta H's to calculate the energy being absorbed or released. So let's take a look at an example to put all of this together. So the question asks, what is the total energy required to increase the temperature of 100 grams of water from negative 5 degrees Celsius to 102 degrees Celsius? Well, the very first thing we have to ask ourselves in order to determine whether or not we can just use Q equals MCAT, because there is a temperature change, right, from minus 5 to 102. So there is a temperature change. So we could possibly just use one Q equals MCAT and be done. But if there is a phase change between negative 5 degrees Celsius and 102 degrees Celsius, then we know we can't just use one Q equals MCAT, and we're going to have to use our molar heats in combination with our Q equals MCATs. And so since this is water and we know that we have phase changes at 0 degrees Celsius and 100 degrees Celsius, we definitely have phase changes happening as we move from negative 5 to 102 degrees Celsius. So unfortunately, we can't just do one Q equals MCAT and be done with it. We actually have to do this in pieces. So how I recommend to approach each of these questions is to set up a graph and graph all of the pieces you have between the two temperatures you're working with. So for this example, I set up the graph at the left to take us from negative 5 degrees Celsius to 102 degrees Celsius. So I know that from negative 5 to 0, my temperature is going to increase, but then once I reach 0, I'm going to have that phase change plateau where my temperature isn't going to change. And then after a certain amount of time, my temperature will increase again to go from 0 to 100, where I'll be in a single phase. And then when I reach 100, I'm going to have another phase change, so another plateau. And then finally, I've got one final piece to go from 100 degrees Celsius to 102 degrees Celsius. So the next thing I want to do is label all of those pieces with the methods that I'm going to use in order to calculate the energies. So remember, everywhere that you have a single phase and a temperature change, you can use your Q equals MCAT. So for this example, I have 3 pieces that I can use Q equals MCAT. Between my negative 5 and 0, where I'm solid water, and then between my 0 and a 100 and my 100 where I'm liquid water, and then finally between my 100 and 102 where I'm water vapor or gaseous water. So now I have 3 out of my 5 pieces labeled with the method that I'm going to use to calculate my energy transfer, my energy required in this case. So now I need to label how I'm going to calculate that energy transfer during my phase changes. So at my 0 degrees Celsius and my 100 degrees Celsius. Well, since I'm adding energy and I'm going from solid to liquid at 0 degrees Celsius, I'm going to use my delta heat of fusion, my molar heat of fusion, or my delta H fuss. And then at my 100 degrees Celsius, since I'm going from liquid to gas, I'm going to use my molar heat of vaporization, or my delta H vap. So now I need to calculate each one of these pieces individually, and then if I take the sum of all of those pieces, that will give me my total energy required to increase my 100 grams of water from -5 degrees Celsius to 102 degrees Celsius. So let's start by calculating our molar heats, our delta H's, since we really haven't had a chance to practice with those. So the very first one on my graph is my delta H fuss, my molar heat of fusion. And for water, that's 6.01 kilojoules per mole, meaning that it takes 6.01 kilojoules to melt 1 mole of solid water. So this is really just a conversion factor, but I need to have moles in order for this to work. And I don't have moles. I have mass. They gave me 100 grams of water, but I can very easily convert from grams of water to moles of water. So I take my 100 grams of water, divide by 18 grams, which is my molar mass of water, and I get 5.56 moles. So now I can use that plus my delta H fuss conversion factor. So I start with my 5.56 moles times my 6.01 kilojoules over 1 mole. My moles are going to cancel, and that's going to give me 33.42 kilojoules. So in order to melt 5.56 moles of water, or 100 grams of water, that's going to require the addition of 33.42 kilojoules of energy. Now I can do the same thing with my delta H vap. So my delta H vap for water is 40.7 kilojoules per mole. So it takes 40.7 kilojoules to vaporize 1 mole of water, or to take 1 mole of water from a liquid to a gas. So first I need to convert my grams to my moles, which I've already done in the first step. So I'm just going to take my 5.56 moles that I've already calculated and use my HVAP conversion factor to convert that into number of kilojoules. So I take 5.56 moles times 40.7 kilojoules over 1 mole. My moles cancel, and I'm left with 226.3 kilojoules. So it takes 226.3 kilojoules to vaporize 5.56 moles, or 100 grams of water. Now we can go on to solve for all of our Q's, our Q1, Q2, and Q3. So the first one we have, our Q1, is when we're in the solid phase and we're going from -5 to 0 degrees. So for all of these, we're going to be using Q equals MCAT. So for Q1, our mass is 100 grams, and our C, we have to be very careful here because so far we've only been using 4.18 joules per gram degree Celsius. But our specific heat actually varies depending on the state that our matter is in. So our specific heat is going to be different for our solid water, liquid water, and gaseous water. So for our solid water, our specific heat is actually 2.108 joules per gram degree Celsius. So that's really important when you're working with water in these Q equals MCATs to make sure that you're using the appropriate specific heat. And so then next for our delta T, remember our delta T is always final minus initial. But the other thing to keep in mind for these Qs is that our final minus initial is not our final temperature or our very initial temperature. It's only the final and the initial temperature for this one piece. So for this one piece, my final temperature is actually 0 and my initial temperature is -5. So my delta T is going to be 0 minus minus 5. So when I put all these in and I get 100 times 2.108 times 5, I get 2,090 joules for Q1. So now I can do the same thing for my Q2. So for that, my mass is still 100 grams, and my specific heat, since I have liquid water this time, my specific heat now is my 4.18 joules per gram degree Celsius. And my delta T is my final minus initial for this one piece only. So for this piece, my final temperature is 100 degrees Celsius, but my initial temperature was 0 degrees Celsius. So 100 minus 0, and my delta T is going to be 100. So 100 times 4.18 times 100, and I get 41,800 joules for my Q2 when I'm in my liquid phase. Finally, for Q3, I do the same thing that I've been doing. So my Q3 equals 100 grams for my mass times my specific heat for gaseous water is 1.996 joules per gram degree Celsius. So I put that in for my specific heat since I'm working with gaseous water for this piece. And then my temperature change, my delta T is final minus initial. And for this piece, my final temperature is 102 degrees Celsius, but my initial temperature was 100 degrees Celsius. So 102 minus 100, so my delta T is just going to be 2. So 100 times 1.996 times 2, and I get a Q of 836 joules. So now all that's left is to add all of my pieces up to get my total energy required to take my water from -5 to 102 degrees Celsius. So my Q1 plus my Q2 plus my Q3 plus my delta H fuss plus my delta H vap. However, if you notice, your delta H values, your delta H values are in kilojoules. So your delta H fuss is 33.42 kilojoules, your delta H vap is 226.3 kilojoules, whereas all of your Q values are in joules. So you need to convert either from joules to kilojoules for your Q or from kilojoules to joules for your delta H's. It doesn't matter which one you go unless they specifically ask, but I recommend converting your Q from joules to kilojoules, as I just find it's easier, and then you're dealing with smaller numbers. So remember, there are 1,000 joules in 1 kilojoule. So for each of your joules, you're just going to divide by 1,000 in order to convert from joules to kilojoules. So Q1 would actually be 2.09 kilojoules. Q2 would be 41.8 kilojoules. And Q3 is going to be 0.836 kilojoules. So now that everything's in the same unit, everything's in kilojoules, I can take my Q1, my 2.09, plus my delta H fuss, which is 33.42, plus my Q2, which is 41.8, plus my delta H vap, which is 226.3, plus finally my Q3, which is 0.836 kilojoules, and I get a total energy requirement of 304.5 kilojoules. And notice that that value should be positive because I need to add energy in order to go from -5 degrees Celsius to 102 degrees Celsius. Well, that concludes our lesson on measuring total energy change. Bring any questions you have with you to class.